Hey guys, good morning all. Just give me a yes in the chat if you guys are able to hear me and see the sublime text. Quickly give me a yes in the chat if all of you guys can hear me and you guys can see the sublime text. All of you can. Cool. Let's quickly start with today's session. Prior to that, have a quick revision what we discussed as part of the last session. So in the last session, we have completed our basics of system design and we start with our case studies. We also talked about the template, which is going to be useful for covering all the case studies as well as discussing with any system design in general between software engineers as well as with the interviewer. Okay. So let's go through that real quick. The last part we were discussing was indexing. There was only one part which was pending, which was data structure used for indexing. So depending upon which type of database, they use different level of indexing based upon different data structure. Most of the SQL base, they use B plus trees for efficient quick lookup, deletion and insertion. Data stored is sorted. Operations are big of log of n. For hash tables, some databases which use indexes hash table, for example, NoSQL databases, mostly like DocumentDB, MongoDB and S3, they use the hash indexes. So in that case, my result of contest is going to be a sorted order. So in this case, it not necessarily needs to be a sorted order, but it's much easier to get the sorted order in terms of using a hash-based indexing. Third is the spatial databases, for example, Redis, geospatial indexing. Wherever we need to find latitudes and longitudes, all those sort of use cases with either static location or dynamic location, R trees are the one to go for. And then we have some databases which work for bitmap index where you have multiple transaction queries running on true or false values. Okay. Then we talked about the system design interview template, which is a step-by-step guide. What is that template regarding? The template is regarding if you have to build any system, how to go in sequence. As I said, it's not a hard and fast template. Feel free to make modifications to it as you are working through the course. First part is we start with the requirement clarification where we clarify about what are the functionalities or the features of the product that we are going to build. Non-function requirements, which includes availability, scalability, consistency, reliability, all of those parts. Okay. And third is the additional requirement, which is good to have, but it's not immediate requirement as of now. Then once we're clear with the requirement, then we go to something called capacity estimation or back of the envelope estimates. What does that mean is we talked about what terms of traffic we are estimating, what queries per second we are estimating, what storage estimate we are estimating, and caching memory estimate we are doing. We talked about from daily active users, monthly active users, transactions per scale, and then we try to make a good sense of judgment about how much size of data I'll be dealing in over a course of 5 or 10 years for that system. Once we do that, then the third next part is talk about system interface or system design APIs, which talks about what are going to be the public APIs that are required. We necessarily do not talk about the internal APIs, but we definitely talk about the customer facing APIs, okay, or something which is functionality APIs. Then we talked about defining the DB schema, which includes type of data to store or the core entities, the choice of database, mapping across different tables or databases. Then finally, we talked about high level design. Once you have these four level of details considered, now you're good in position to start with the high level design. 95% of the design that you'll be working with or you'll be building with, it's going to include this kind of architecture, which is N-tier architecture in general, which talk about the user management, which talk about the client flow, which talks about the business management, etc., etc. Okay, so a client, an API gateway, services, server, application server, databases, caching, load balancing. More or less, this is what you'll be doing. And then we sixth about the component level design. Once we have got this high level design, now we can deep dive further into services, what sort of services, how they interact with each other, caching, CD and DB partitioning. Then we finally talked about bottlenecks and trade-offs. If my current design introduced any SPOF, how do we fix that? What choice of tech stack? What's the reasoning behind that choice of tech stack? So on and so forth. Auto scaling, error exception scenarios, etc. etc. Then we have telemetry analytics, including monitoring and performance. And finally, that was a template that we have finished. On that note, we start with the first case study that we are going to continue now, which is designing a URL shortening service like TinyURL. First thing first, what's the purpose of a URL shortening service? It takes a long URL. You go to that app, whether it's a web app or some other sort of application, that is going to generate you a short URL, which is of 6 to 8 characters. In your browser, if you go to that short URL or type that short URL, it will take you back to the long URL, original long URL. Okay. Some of the similar services include TinyURL, bit.ly, Google has its own, and there's QLink as well. Okay. We talked about a demo to understand that better, how it converts long URL to short URL and vice versa. So first part question comes, why do we need such kind of service in the first place? Although this is not part of the system design, but this is important to understand why do we need URL shortening or what use cases URL shortening is actually solving for. First thing is, if you're sharing somebody to have a short URL, it's much easier to use with less typos or mistakes as compared to a long URL. Second, on some platforms, they have a limit on character size, right? So in such case, example for Twitter, if there's a limit on character size, then we can generate a short URL for it. Third, it's very important in terms of affiliate marketing, because if you're going to share a big link with someone, nobody's going to click on it. So you share a small link which can help you with and analyzing the audience, the tracking, the campaign performance, etc., etc. Okay. Now we move to the actual system design, which starts with requirement gathering. So we talked about the function requirement. It's a long URL. You should be able to convert into a short URL, which is unique. Another way of putting that is going to be 1:1 mapping between a long URL and short URL. When that short URL exists, it should redirect to the long URL, and each link will have a default expiry time of 5 years. Okay. Then we talked about non-function requirement. My system should be extremely highly available. Why? If my system is not available, if there is any downtime in the system, that means all the URL redirects from short to long will not happen. So customer will not be able to go to the link that we have shared via TinyURL. Second, your direction should happen in the real time. So having a very real time kind of a scenario with minimum latency is very, very important to my system. Third is additional or extended requirements, which is user can pick a custom URL, they can mention the expiry time. We can have some analytics redirections, and we can have a third party integration. All of these are additional scope. Then we move to the capacity estimation or back of the numbers estimation to understand what sort of numbers we are talking about here. So first I clarify the difference between a read heavy application versus a write heavy application. If you get more number of reads as compared to write, it's called read heavy. Other way around, it's called write heavy. Okay. So first thing first, my system is definitely a read heavy application. So we kept the ratio of 100:1. Let's say for every redirect, for every write which is done from long URL to short URL, there is 100 reads which is done for that. Okay. Then we move to traffic estimates. Let's start with some baseline assumption. Baseline assumption is in 1 month across the globe, I'm getting 500 million write requests. So with the read write request of 100:1, number of read calls in a month would become 50 billion. Now, if I talk about that scale in queries per second, in queries per second, I'm talking about 200 URL per second, which is being created. That's a write case. Or a read case is 20,000 URL redirections per second. Then we talked about storage estimates. What the storage estimate refers here? Storage estimate refers here is, since my URL is going to be stored for 5 years, if I talk about 500 million URLs, 12 months, 5 years, that's going to be 30 billion URLs that I need to store. Okay. 30 billion URLs, size for 8 characters, 16 bytes, assuming that we are storing some additional data like user ID, location, creation time, expiry time, etc. More or less, it will never cross the value of 500 bytes for me. So one URL 500 bytes, 30 billion URLs you want to store means 15 terabytes for 5 years, which is decent. 15 terabytes for 5 years, let's say 3 terabytes per year. It's not extremely large memory. I can store that in a hard disk as well. Okay. Then we talked about cache memory estimates. What sort of cache memory will do? There we talked about an important rule called 80-20 rule. Means 80% of my request is generated from 20% of my data. So I don't need to store all the time, all the data in it. Again, cache is not a database. Cache is a short-term memory. We usually keep the cache for 24 hours or 48 hours at max so that we can refresh the cache every time. Okay. So 20K read requests per second for 1 day. That is 1.7 billion read requests for per day. That's why we are interested in the per day data. Out of that per day data, I'll take the part of 20%. So 170 GB of cache memory we would need. Okay. Per day we are talking about here. Or overall 0.2%. So 170 GB you need for the cache memory. Now, in terms of system API, there's going to be a post call where I'm converting the long URL to short URL. And in terms of a get call, I'm getting that long URL back from the short URL. And now we're going to continue with defining the DB schema. But before I go with this, everybody crystal clear with the revision, give me clear in the chat. Come on guys, be quick. Any doubts, any questions, let me know. If everybody's good, give me clear in the chat. All right, now we move to the step number 5, which is defining the DB schema. In terms of defining the DB schema, there are 3 parameters we would like to talk about. Analyze the type of data you want to store or what core entities in the system. Then make a decision to the choice of database. Then talk about mapping across different tables or databases. Okay, so we need to make some observations before we can actually make a decision. What are those observations? Number 1, we need to store billions of records. That's for sure. 30 billion records we are talking about, 30 billion URLs we are talking about. So we need to store billions of records. Okay. When we give short URL, it should give redirected write. Do we handle redirect in URLs or redirect 300 to redirect? When we give short URL, it should get redirected write. Yeah, it will get redirected. Do we handle redirection in UI or server will send it through? We handle that redirection in UI, but of course that redirection is coming from some server, right? That server is our TinyURL service. Okay. Number two. First, we want to store billions of records. Second, in cache calculation, only read calls we will calculate. Yes. I mean, total number of calls we are talking about here, right? If you look at the cache calculation, we talked about the total number of read requests which is coming from. The purpose of cache is from the read itself. Okay. We are not actually writing in the cache. Cache is the purpose is you will get the most frequently accessed data. So we are more interested in the read traffic here. Second, each object we store is small. Small means what? 500 bytes. All of these things are required to be put under observation so we can make a decision what choice of database would be best here. There are no relationships between records. Between records. One moment. The application will be applicable for on-prem application also. Yeah, cloud on-prem doesn't make any difference here. We are talking about a system design. You can host it anywhere in any technology you want. Okay. So records apart from whom? Apart from user, which has created the or user who has created the URL. And number four, our service is read heavy. All of these are key pivot element to make the decision of database we want. Are you storing the long URLs? If not, then how are we redirecting to CurtWell? We'll come to it, guys. We'll come to it eventually. To give your answer, we are not storing it. What sort of mapping we are using? That's what we're going to talk about step by step. So first thing first, we need to store every billions of records. Let's make some observation about the system we are trying to build. 30 billion URLs we talked about over a period of 5 years. So we need billions of records. Makes sense. Each object is relatively small, almost 500 bytes. There are no relationships between records. This is important factor. There is a user who has created the URL. We do not have 10, 20, 50 different kind of tables or entities in our system. We basically have two entities. One is a user, one is a URL, right? And the only relationship that we want is between user and URL. Okay. Our service is extremely read heavy. That also we not about. Okay. Now coming to DB schema part. In terms of DB schema, more or less, I just need two tables or two schemas, however you want to call it. Table 1, table 2. For a URL, what would I need? I would need a short URL. Let's call that as hash, which is going to be my primary key. I'm going to keep my original URL here, varchar, which is what we call as long URL. Number 3, I can put a creation time. That can be of timestamp. I can keep expiration time, which will be a timestamp. And of course, user ID means who is the one which has actually created this URL. And if I talk about table 2, I would need the user UID, which is going to be a primary key. Maybe the name varchar and the email, let's say varchar or string, whatever you want to call. This should be integer, that should be fine. Okay. This DB schema part clear to all? One moment, guys. This DB schema part clear to all? We'll talk about it. How will we capture those user details? All of these we'll talk about. Let's go step by step, guys. What we are currently discussing, what is going to be the DB schema? That's what I'm coming to, guys. We'll talk about it one by one. There will be cases when we did not log in. There will be cases when we did log in. We'll talk about all of that eventually. Okay. But on the overview level, this is something that I will need to store. Two schemas. One is talking about the URL. One is talking about the user. Okay. And these are the observation that we had. Now, based upon this detail, let's make a decision on choice of database. choice of database. Okay. Yes, that's what I'm saying. Eventually, in the final design, we will not store that. Okay, understand this one way. We never start with the correct answer. What we do is we eventually start building system in one way. Once we start building it, we'll realize there is something wrong. That may pivot the change and we move to a better approach. And that's the actual way of building the system. If you directly start with building the system with the final answer, you will never able to understand what exactly was wrong in the previous approach. So all of these that we are learning, we are going to pivot it. This is not the final design. Just wait for a moment. And in general, for all the 10 case studies, we will have step 1, step 2, step 3. You'll start with first design, you'll identify problems, you'll move to second design, you'll identify problems, you'll possibly move to third or fourth design, that is your final design. Okay. So whatever you're seeing right now is not the final design. So have patience. We'll talk about all the problems. We'll talk about all the solutions. Okay. Coming on these data sets that we have as of now, from these data points at this moment, which are on the screen, let's make a decision on the choice of database. I know I have a very fixed schema, and that schema is pretty much not going to change. It's not a flexible schema. I don't have much relationships between or too many complex relationship like joins or something like that. My service is very read heavy. I'm storing a very small data in terms of the size, but I'm storing billions of records. All of these anticipations, I can easily choose either a SQL database or NoSQL database. SQL database would be more helpful in case I'm talking about much higher queries, much higher joins. In this case, that is not really the requirement. Okay. So since we anticipate storing billions of records, and we don't need to use relationships between them too much. We can go ahead with, or instead of calling it ideal, we can go ahead with suitable database, let's say NoSQL DB. Okay. So our use case can be here a MongoDB, it can be S3, any of them. Okay. In general, any NoSQL database would be able to serve a purpose here. Okay. We don't need to use much relationship between the table. That's the right term. Original URL be of fine length. What length are we going to give to that varchar? Usually there's going to be upper limit. Either it's 255 for some other characters, but there's going to be an upper limit. Okay, it cannot be an infinite length for sure. We can configure that. That being said, this part clear to all. This part clear to all. Fifth part till the defining DB schema. Okay. Now we are going to further deep dive into some component of it and understand what can possibly go wrong with this approach and then try to fix it one by one. So sixth part, I'm going a bit deep dive, which I'm calling as algorithms. Okay. Remember, one of the key function requirement of my system was I should be able to generate a unique short key ID. Remember, 1:1 mapping, a short URL which is unique. How exactly I'm going to do that? What sort of algorithms I'm going to use that? A key component is how do you generate a short and unique URL? So every time a request comes, and every time is again subjective, every time can be coming from the same user, every time can be coming from different users. But every time a request comes, how do you make sure you're generating a short and unique URL? Okay, let's talk about it. When I say short, I'm referring to 6 to 8 characters, not more than that. There are multiple ways to do it. Let's talk about each step. Let's talk about each of the ways and see what can be possibly right and wrong with that. One easy way is I can start with encoding the actual URL, or another way is hashing. What does that mean? Whenever I get a long URL, I can compute a unique hash of the given URL. Okay. And that hash can be used for encoding, and displaying. Okay. The algorithm that we can use for hashing, there are many. Common ones are MD5, SHA-256, SHA-512, depending upon what is the maximum length that we want to do, base 64, encoding, etc., etc. Okay. And display in short URL that I need to do, that is going to be alphanumeric only. What do you mean by alphanumeric values? These tiny URLs that I'm going to generate, which is going to be of 6 to 8 characters, they're only going to contain A to Z, capital A to capital Z, or 0 to 9. That's it. We are not talking about any hash or percentage or spaces or any other additional characters. Okay. Yeah, that's what we are coming to. That's what we are coming to decision, whether we need to make 6 characters, whether we need to make 8 characters. Okay. So A to Z is 26. Capital A to capital Z is again 26. 0 to 9 is 10 characters. So total how much values I got? Total how much I got is 62 characters. Okay. Now this becomes the problem statement of permutation and combination. Whether I have to make a 6 or 8 characters, that decision will be made here. How that decision will be made here? Let's talk about it. If I keep a short URL of 6 characters, okay, means my total combinations would be what? Think of 1, 2, 3, 4, 5, 6. There are 6 seats that you can fill, and each of the seat you can fill in 62 ways. Any of these values, which is totally 62 ways. How many possible combinations? Come on guys, simple permutation combinations question. 6 seats are there. Each seat can be filled by 62 ways. What's the total number of seats we are talking about? Come on guys, be quick. Okay. It's very simple guys, nothing to complicate here. This can be filled by 62 ways, agree. First seat can be filled by 62 ways. Second can be filled by 62 ways. Third can be filled by 62, fourth, fifth, and sixth. And my tiny URL can definitely contain something like this. tinyurl.com/AAAAA. This is a completely valid tiny URL. When we talk about unique, we talk about the unique in the sense this should point to only one website. That's what you mean by unique. Doesn't mean that the string has to be unique as well. Okay. So if everything can be filled by 62 ways, total number of combination will become 62 raised to the power 6 combinations. All agree? Total number of ways will become 62 raised to the power 6. If I take 8 characters, I would add 2 more here, 7, 8. That will become 62 raised to the power 8. Everybody crystal clear with this first. If you choose 6, it will be 62 raised to the power 6. If you choose 8, it will be 62 raised to the power 8. Now coming to a decision, should I stick to 6 or should I stick to 8? That decision is right here on your screen. 62 raised to the power 6 is roughly 60 billion strings. Strings, short URLs, whatever you want to call. 62 raised to the power 8 is roughly equal to 260 trillions strings or URLs. Now, go back to where we started. We started our requirement that over a period of 5 years, we would need 30 billion URLs. Agree? Over a period of 5 years, we would need 30 billion URLs. That is the pivot decision that I will make here. If I need 30 billion URLs, do I need to store 260 trillion? Do I need to go with the approach which can make 260 trillion? No, it's highly unlikely. Even the scale increases, still more than double is still being there in 60 billion URLs. So for our use case, for 5 years, we need 30 billion URLs. Hence, we are good with 6 characters here. All agree with this? Come on, guys, quick in the chat. Okay. Now let's talk about the next part. So we're good with this part. My combination that I'm going to build in terms of I'm going to build with hashing or in general other approach that I'm going to use, 6 characters sufficient enough to solve my use case. Yeah, the scale becomes extremely large that we can go with 8 characters. Now, coming back to the actual problem statement, what did we talk about is how are we generating short and unique URLs? We are going to take a encoding of it or we are going to take a hashing of it. So if an original or long URL will come, I am going to encode it. I am going to make the short URL out of it. This is what we discussed so far. All agree? All agree? As part of first approach, this is what we discussed. Do you see any possible issue with this approach? Not with this one. I'm talking about this one. Do you see any possible issue with this approach? If yes, what issue do you see? Quick in the chat, guys. Need to store the hash. The hash is the short URL. Hash collision. Okay. Let's say we're encoding everything. Think it in simple way, guys. You got a long URL, you make a hash, you take a encoding out of it, and then you are converting into a short URL. That's it. Do you see any problem in this? Come on, guys, quick in the chat. Encoding might be same for two different URLs. No. So the way MD5, let me answer that question. The way MD5 or any of these encoding pattern works is it's a one-way transaction. One-way transaction means if you convert A to B encoding, you cannot get B to A. Okay. So uniqueness part will not come into this space. But there is two major issues here. Okay, let's talk about the two issues. Some of you have got the first issue correct. Second issue nobody has talked about. That is also a very critical issue. First issue is that if you are barely doing a hash encoding on a long URL to a short URL, it's going to lead multiple problems. If multiple users enter the same URL, they will get same shortened URL. All agree? Why? Because my MD5 or SHA-256 or whatever algorithm that you have used, SHA-512 or whatever that you have used, will create the same hash for same input for different users. What does that mean? Take an example. The website is google.com. Let's say there is a user A and there is a user B. Now what happens in such use cases? User A goes, user A says, hey, I want to generate a short URL for google.com. So let's say SHA-256, for example. It can be any of the encoding algorithm. It converted X, Y, Z, A, B, C. Okay. And user B goes, we'll talk about it, guys. We'll talk about one by one. Google.com, again, it will generate X, Y, Z, A by C. All agree with this statement. If we are blindly might be the wrong word, but if we are directly taking the encoding over the long URL and generating an encoding of that, means whatever algorithm we use, doesn't matter, it's not dependent on the algorithm, it's always going to generate the same output because input is same. All agree with this. Okay. So that means if multiple users, one moment, guys, if multiple, yeah, that's what I'm coming to. If multiple users are trying to convert a tiny URL for a website or a particular resource, it's going to give them the same result. Do we want that output? The question that you asked, that is the answer I'm giving. Do we want for multiple requests to generate the same output? The answer is no. Maybe one optimization that you can think or talk about with your interviewer or anything in general while designing is, as long as it's the same URL, one moment, as long as the same URL, same user asking for the same website, we can then return the same result. Okay, that can be one extreme optimization if you want to further deep dive into. But overall, if multiple users, one moment guys, if multiple users are coming with the same request, expectation is they will get the different URLs. So if I generate a google.com tiny URL, you generate a google.com tiny URL, somebody else generate a tinygoogle.com, they should be completely three different URLs. It's not the same URL which needs to be posted. This part clear? This part crystal clear to all. That's the expectation of our system. Okay. Now, what do we need here is, one moment, guys. What is the problem in giving the same tiny URL? Then, okay, understand. The whole part of TinyURL is not mapped to just the website as a resource. It's mapped to the user as a resource as well. Okay. If you have converted a website and its corresponding tiny URL, then there is no use of this tiny URL tool altogether. Then it's just a dictionary, long URL, short URL. That's it. Then you have made it standard across the globe. This long website has this short tiny URL. What's the part of user come into this place now? Think logically. If for every website, let's say google.com has tinyurl.com/abc. If we make it for all the websites, in that case, what's the part of customer comes into picture? What's the part of user comes into picture? How do you get to know which user has converted this? Because if everybody is having the same link, how would you track the affiliate marketing and all the metrics that we need to track? Okay. This resource, go back to the initial requirements. The whole idea of this resource was, why do we need this URL mapping? The whole idea of this resource was, we want to make sure it's a user specific as well. Okay. All right. Now coming back to this, what is our need? The need is, if it is same input from different users, it should generate different short URLs. Okay. Now that was one problem. There is another problem which nobody talked about, which I was expecting somebody will talk about. This approach talks about a long URL comes, you put an encoding, that encoding will give you a short URL, right? We identify one problem in that. Second major problem is in that encoding that you are doing, that encoding is going to introduce some latency. Yes or no? You take a long URL, you generate a hash, that hash will create a tiny URL. The system that we are trying to build here, it's a very important requirement that I am able to redirect it in short time. The moment I press a long URL, I want the short URL immediately now. I'm not going to wait for a short URL to be generated 3 seconds or 5 seconds. It's not a asynchronous flow. We are talking about a completely synchronous process here. Okay. We're talking about it, guys. We'll talk about one by one. So a system goes to long URL, then you go to hashing or encoding. Okay. There is an extra latency which is introduced while encoding. And number two, hashing is generated on the go. You call it on the go or you call it on the fly, same terms. Okay. Basically, the term is generated in runtime. Since your hashing is generated in the runtime, it's going to introduce some extra latency, which we do not want. We don't want in real time. Coming to your question part, we could pre-compute and save it in database and use it. Until and unless a long URL comes to your system, how are you going to pre-compute it? How do you know which long URL I'm going to convert to a short URL? The encoding is on the long URL. So until and unless that request does not come into system, you cannot pre-compute it. Okay. So coming back, these are the two problem statements. Number one, if multiple users come, they're going to get the same shortened URL, which we do not want. And number two, there is a latency part which is introduced. Everybody clear with these two problem statements? Then we'll talk about solutions. Come on, guys, quick in the chat. Okay, cool. If this is good, Now let's talk about workarounds for this. We'll take the problem one by one, we'll dissect the problem, we'll come to the solution one by one. Let's talk about first problem. Problem number one. Problem number one is, what if multiple users enter the same URL, they're getting the same shortened URL? Before I give my answer, you guys tell me, what do you think can be the possible solution for it? You're clear with the problem? Let me know what's possible solution you think would be there. And by the way, when I say possible solution, we are not changing the encoding approach. Still keeping the encoding approach. What do you think is the possible solution? Okay. When you say timestamp, what about the race condition in timestamp? What if two customers or two users try to create the same long URL at the same time? Come on, guys, quick in the chat. Okay, cool. Anybody else? Cool. Let's discuss the solutions. Let's take one by one. A and B. There are two ways to work around it. Of course, one would be a good way, one would not be a good way. That's what we're going to talk about. If I have to talk about keeping it a unique, the whole idea is I want to keep it unique. So what I can do is I am going to add some user identification to make it unique. Okay. So my key can be made like user ID, user ID plus the timestamp plus the actual long URL. Now this is going to be a unique key for encoding. All agree with this? All agree with this? Cool. Okay, let's discuss one more thing here since somebody asked. Now the question is, okay, why do we need the timestamp is same user try to create the long URL for two different times. It's still going to be the same if you don't include the timestamp. For example, the user ID is 123 and the long URL can be something different. What if happens if multiple users are going to create it? The whole idea is to make it unique. You already answered it, got it. So I'm not going into details. Anyways, somebody asked this question. So let's answer that part as well. This user UID, it's easier to get the user UID for the people who have registered into the account. They log in, then they create it. But think it from a customer standpoint. Do you want to force everyone to log in first and then create a short URL? Idea is no. Bit.ly does that. That's why if you remember, I started with bit.ly. I'll come to the solution part, guys. I started with the bit.ly, but I didn't want to register it. So I didn't want to give the details. That's why I moved to TinyURL. So in a customer experience, again, it's business decision mostly, but as an engineer, you can think of for a customer experience, I don't want to limit. I don't want to limit anyone to use a particular, create an account, register it, then give me the user ID. So if you don't want to give that, if a customer is logged in, you can immediately capture the user ID. If they are not logged in, what are you going to capture? You can capture their XSRF token. Okay. Current session token, you can get it from their cookies, XSRF token that is going to be unique for a particular resource they're trying to access, and that's it. This XSRF token is always going to be unique. That's going to guarantee it's going to be unique always. Okay. So that solves part of my problem. What if multiple users try to answer the same URL? They still will get a different encoding. This part clear to all? Can't we use queries based on short URL hash and user ID based on it we can create it or not? We'll talk about it. Okay. Yes, XRS token will be unique. Each request. Each request it will be unique. Okay. See, XSRF is a session based. So every time you create a session, every time you make a request for that particular request, it will be unique. Okay. All right. Coming to number B, what can be the other approach? Let's talk about other approach also. I can add a counter or a sequence number to make it unique. The idea was to make it unique. Remember that. Okay. So let's say first time google.com came. Whichever user, whichever time, I can create something like this: https tinyurl.com, let's say ABCDA1. Next time comes paste, 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 paste. Make it 2, make it 3, make it 4, make it 5. Do you see any problem with that? Okay, correct. There are two problems. First, definitely we need to keep a counter, but counter is less of a trouble because eventually we can have the primary ID being indexing +1. So that's not a bigger deal. The even bigger deal is this part. When we are talking about a scales of billions of records, or let's say 20,000 reads per second and 200 writes per second, such a big scale for very large numbers. Let's say a particular website has been shortened multiple amounts of time. When I say multiple, I'm talking about thousands and millions amount of times. For very large number of shortenings, my sequence number will be very large. Okay. So that's a drawback here. So this might not be a completely good approach. It's one of the approach, but not a good approach. So what's a good approach till so far? If you're sticking with the encoding part, what's a good approach so far? I'm going to log in my user ID either based upon XSRF or actually based upon user ID plus the timestamp plus the long URL that is going to make it a unique key. From that unique key, I'm going to create an encoding. That encoding won't be for the TinyURL. This part crystal clear to all. This part crystal clear to all. Okay. If this part is clear, now is the first part of the HLD diagram for using encoding method. Remember what I said? There is never one moment. There is never going to be a one complete diagram. It's going to be in phases. We'll identify a problem, we'll fix it, we'll move to second phase and phase 3 and phase 4 and so on and so forth. And that's how systems are built. So let's take a look at our first model, which we talked about for encoding based approach. I'm going to share my screen. There you go. Okay, let's talk about it here. Can you please explain why we need timestamp in first workaround? If same user request for short URL for same long URL, it should return the same short URL. But if add timestamp, that will return different. See, that's the use case we want to design. For our request, even if the request is coming from the same user or different user, the request is new every time. That's why we're keeping a timestamp here. Okay. Yes, we are discussing it now. We'll discuss everything. Okay. All right. Coming to this part now. This is the first approach which we talked about in terms of URL encoding part. So what happens? The client makes a request to shorten a URL, goes to server goes to some sort of database. What the database is going to keep? It's going to encode the URL. Once you encode the URL, this is the logic for encoding. Whatever MD5, SHA-256 or whatever you're going to do, that service will take care of the encoding logic. Once you encode it, it's just going to store the encoded URL here, which is what we call as TinyURL. So once we got the TinyURL, we'll return back to the server will return back to the client. Simple end-to-end flow of client and server with encoding method. This part crystal clear to all. Come on guys, speak in the chat. This part crystal clear to all. Okay. Let me close this. Let's go back to our Sublime text and go back to the problem we were solving. Okay, back here. Cool. Remember the two problems or the two issues we identified. The first issue is multiple users, same URL, short URL, same get shortened URL. This is solved. We solved based upon making it unique. Good. What about the second? Okay, any doubt on the first issue? Any doubt on the first issue? Duplication means if we didn't make it unique, that was the duplication part, which we fixed it here. Okay. Now, second issue. How will you solve the second issue? Second issue is equally important as the first one. When the moment you have introduced hashing and encoding, even though let's say you make it unique, so you're not dealing with the problems of duplicates, still it's a latency that you have introduced because every incoming request would now need to first hash first, which is the encoding part that you saw in the diagram. Then it will be inserted in the database, then it will be fetched and given back to the client. How will you solve that part? Anyone? Problem is clear to all? Once you create hashing on the go, okay, problem is clear, so I will not explain the problem. What do you think how you can solve it? Okay, so you think like changing in hashing mechanism can fix it? Okay, that can be one way to think about it. What else? Come on, guys, be quick. No one? Okay, can we already have a 62 character? We'll talk about it. Can we respond concurrently to client and save in DB? Respond concurrently to client and save in DB is not a good way. The reason is if the write in DB fails and you have responded back to the client, next time that request will not be reliable because it's never in your DB. So it's not a good solution. Okay. What else? Scaling. Okay. 10 more seconds, guys. Anybody else? Okay. All right, guys. Last 5 seconds. Enough time. Cool. Let's discuss the answer. Guys, understand one thing. Do not over-engineer any kind of solution. Do not over-engineer any kind of system design. Okay. I have heard pretty much all the terms which can be used in system design, including async approach, caching, CDN, various different messaging queues and answers. Before you even go into that part, identify what is the root cause. The moment you'll identify the root cause, then you can talk about the solutions. Okay. What is the root cause of this problem? The root cause of this problem is hashing. I am doing the hashing. Since I'm doing the hashing, that's why I need to wait in the long time or basically on the go or on the fly, and that's why the latency is introduced. All agree with this part first. The root cause is hashing. There is no other root cause of this. If there is no hashing, there is no latency. Okay, that is part one. Now, part two of it. There can be two things you can go from here. First, if you have to stick with hashing, what you can solve about it. If you don't have to stick with hashing, what's the alternative you can think about it? Okay, so let's start with the first part. If I stick with hashing, I'm able to solve the first problem here, which is great, no doubt about it. But if I stick with hashing, can I solve this second problem here? If I still want to hash it, can I solve the second problem? The answer is no, you cannot. Because the moment you are going to hash, irrespective of whichever algorithm you will use, it will introduce some latency. And the problem is you are doing it on the request. Means until and unless a customer comes with a long URL, you do not know what to hash upon. So it's impossible for you to create some sort of offline kind of a database or offline kind of a mapping where you assume there would be a long URL and mapping will be an encoding. It's impossible. You don't know what a customer is going to come with the long URL. Yeah, you can say that I'm going to index every URL available on the earth. That is not possible. You're not going to build that, right? So till the time I don't get a long URL, I do not hit it in my system and I do not get a mapping out of it, I have no idea about what this long URL is going to be. So there is no possibility of thinking of an offline solution here specific to hashing. This part clear to all? Come on guys, quick in the chat. Okay. Before you give the solution, identify the root cause first. The root cause is hashing here. Okay. One moment. The root cause is hashing here. So two things. Hashing first problem, which was unique generations, that is solved. Okay. We have already solved that. But hashing second problem, which is latency, that is not solved. Why that is not solved? Because long URL will be given at the runtime. If you are taking a hashing of it, irrespective of whatever algorithm you use, that is going to introduce some latency for sure. Is this part crystal clear to all? Okay. Now coming to the second solution I talk about. If you cannot do anything about hashing, why not to think outside the box? Why to stick to hashing? That's how you build the system. You take one approach, you go and deep dive into it, you identify this can be the possible problem, then you pivot back and think of other approaches. Okay. System design is never built with one solution or one approach. Understand this very clearly. It's always subjective in nature. You choose one approach, it might look good, but then once you go deep dive into it, you will identify there are problems with this. And then you will come back and pivot the elements. Okay. You will fix the things which can be fixed in that approach, but there would be some things which cannot be fixed in that approach. Then you have to make a pivot on the decision. So coming to the second part, what's the solution for it? The solution is don't go for hashing. So we will go for something called short URL. One moment. Offline generation. I'm going to generate these short URLs offline. Okay. Can we use the random UID generator instead of hashing? We can give a secret generating. That's what we are talking about. Okay. So instead of hashing, I'm going to create these 6 to 8 characters, whatever number of characters we decided offline. So here does my solution comes into picture. I'm going to have a KGS, which is my key generation service. What's the responsibility of this service? It's going to generate random 6 characters beforehand. So irrespective whether request has come or it has not come, I already have the list of these random 6 characters beforehand and store them in a database, which is going to be a separate database. It's going to be my key database. Why I'm calling it a separate database? Because it has nothing to do with the long URL yet. Even if a request has come or not, it is generating offline. So it is on my servers, irrespective whether request has actually come or not. Okay. Whenever a request comes, a request for a shortening URL comes, just take one of the pre-generated keys and use it. That's what we are going to build it. Okay. Think of it a simple example if you want to understand in real life. The use case of ordering something with Flipkart versus ordering something with Blinkit, right? One moment, guys. If the use case of if you're going to order some with Flipkart, they need to find it, they need to fetch it, that will going to give you 2 to 3 days on delivery. But in Blinkit, it's already available. So they just give you nearest which is available to you and provide it to you. It's not real time, but I'm just trying to explain the difference between the two here. If I have these 6 characters sequence already generated with me, whenever request comes, I can take the first one or whatever the available one and I can give it to the request answer. This part crystal clear to all. The solution we are proposing is here is we generate these 6 character sequences, we store them in a key database. Whenever any request comes for shortening, we take the first one which is available and we just give it to that request. Okay. Yes, that's going to need another DB space. That's why I specifically talked about key database. Okay. How will we make sure that we randomly? We'll talk about. See, there are problems and solutions. There are questions and answers. We need to talk about every approach. That's what we'll go one by one. Okay. Cool. Let's go one by one. Advantages. Advantages is first thing first, we solved the problem that we were trying to solve. One moment, guys. We solved the problem that we were trying to solve. The problem was introduce latency on the go. This is extremely fast one because I'm not creating any time at the go. It's already been created. Request come, it picks the response, goes back. That's it. I am not creating on the go. These are pre-generated keys. One moment, guys. One moment. I will answer everything. Okay. There is no need to worry about duplicates here. When I say duplicate, understand what do you mean by duplicate. Duplicate does not mean that I would generate the duplicate keys. That will be taken care by the key generation service. The key will be unique. That will be taken care by the key generation service. I'm talking about the duplicates. Multiple requests can never refer to the same key because once a key is used, we are going to mark that is used or marked for use or marked for some transaction log. But every time for a new request, it's going to have a different key. This part clear? Every time for a different request, it will have a different key. So there is no possibility of duplicates. There is no possibility in the case multiple long URLs can refer to a same short URL. It's impossible in this case. Okay. No collision, same thing. And my key generation service will make sure that all the keys that are inserted in my KDB, they are unique. That is the job of key generation service. Okay. Now, this solution looks good on the overview part. Let's deep dive into it and see if there are any possible caveats that we need to talk about it. Okay. First thing first, it did solve a lot of problem for sure. The problem that we encountered with hashing, it has solved majority of them. But what about concurrency? Okay. When we say what about concurrency, means as soon as a key is used, it should be immediately marked in the key DB to ensure it's not reused. What you don't want to do is you do not want to give the same key. Key means 6 characters we're talking about. You do not want to give the same key to 2 different requests, right? So way to do that is the moment a key is used, one request comes, you got that particular 6 character combination. Now, anytime next request comes or any other request come, that 6 character is not available for used. This part clear to all? Okay. Understand this in a real life example. If somebody booked a movie ticket, that seat has become gray now. You cannot book that. Does that make sense? If somebody booked a particular seat in the movie ticket, that seat has become gray, nobody else can book it now. Some sort of same logic, but in a much faster read write calls. Because this is going to be done in, let's say, that we talked about 20,000 reads per second, right? And 200 writes happening per second. I need to implement it in such a way that if there are multiple concurrent calls happening, I will make sure at the transaction level, if something is picked up, it's not going to be reused. Okay. If there are multiple servers, reading keys concurrently, or actually we can remove this. We don't need this. Think of this as key database. We got key 1, we got key 2, key 3, key 4, key 5. And we have this key database. Okay. Now two requests come together. Let's say request 1 and request 2. Two requests come at the same time, which is a very high possibility. How would you determine which request will go to, or which key 1? Key 1 can be only mapped to one of this. Key 1 can be either mapped to request 1 or key 1 can be either mapped to request 2. Both of them come at the same time. What will happen in that case is, this is the concurrency problem we are talking about. What do I need to make sure? I need to make sure it's a unique mapping, and I need to make sure that it is synchronized. Okay. So how are you going to implement this solution now? Problem is clear. We'll talk about it. Problem is clear first. One moment, guys. Problem is clear. Before you give the answers, make sure the problem is clear. Multiple requests come at the same time. Obviously, you can give one key to one request. How would you solve it now? Okay. Repeating the problem statement. You have this key database. Let's take key 1. At this moment, two requests come at the same time. Exactly same timestamp, two requests comes. My key generation has to be unique. So this key 1 can either point to with request 1 or it can either point to request 2. It cannot point to both. How would you make sure if multiple requests come? I've just taken 2 for example. If multiple requests come, this remains transactional in nature. Means it either maps to key 1 or it's mapped to request 2. That's it. Come on guys, anybody? What's the solution for it? Okay. Exact same timestamp. That's what I said. The concurrency is when you have the exact same timestamp. Come on guys, quick in the chat, then let me know. Cool, let's discuss the answer. So what we need to do is, there are multiple ways to solve this question. There is two things I would like to talk about. This is pretty much the situation which will happen in the case of Make My Trip, Booking.com, or any kind of booking service you have booking, or even Ticketmaster. We'll ideally talk about more in terms of logs in Ticketmaster because that makes more sense to talk about it here. Okay. Optimistic logs, all CC and everything, we'll discuss more in detail here. I'm not discussing that in detail here because not relevant for this particular case. Okay. That will be much more relevant in the case when you're designing Ticketmaster, Booking.com, such kind of things. Then it makes more sense to go deep dive into it. But I'll cover whatever is the answer there is the same answer here. Okay. First thing first, I am going to keep my key generation service synchronized. What do you mean by synchronized is my server can use key generation service to read or mark the keys in database. What does that mean? As soon as a key is used, and this is the non-currency case I'm talking about, as soon as a key is used, let's say the request key 1 is used, we need to mark somehow flag the key as unavailable. Either you can use a flag like this, is already flagged, and make it as true or false. Okay. If as long as one key is used, I want to make sure my server which will come for asking for a request here it would know very well that key 1 is already taken. One way of doing that is I can introduce a flag and I can mark the flag as true here. This statement clear to all? We'll talk about it, guys, one by one. This statement clear to all. So this is part of the problem where we are talking about how not to use already used keys. Nothing to do with concurrency here, just the problem I'm talking about, how to make sure that you're not using the key which is already introduced. So you need some sort of logic. A simple way of doing that logic is you can use a flag, you can create is already flagged here. So in my key database, apart from the key which has multiple columns, I can add one more column which is already flagged, mark it as true or false for every record. Next time when a request would come, it will read that record first. If it is not already flagged, I can keep that in my service layer. If it is not already flagged, then I will going to associate with the next request. This statement clear to all? Come on guys, quick in the chat. Okay. This is an acceptable solution. If you talk this in interview or if you talk in this in general design, this is an acceptable solution. There is, I can go deep dive into it. This is an acceptable solution. There's nothing wrong in the solution. But guys, okay, again, you're confusing two things. I'm not talking about concurrency here. The problem is this here. Let me highlight it. Concurrency, I'll talk about here. Okay, let's keep it very different. Concurrency solution. Let me write it like this. Okay. I am not referring to concurrency here, making it very clear. Concurrency solution we'll talk in the second part. I'm talking about the case. In your key database, you have the key. How would you make sure that you do not reuse the same key? This is the problem statement we are talking about. Okay. So to avoid reusing the same keys, what we can do is we can create another column which is already flagged or is already used. Kind of this is already used makes more sense. And then you can mark it as true or false. And your service will check if the key is not already used, then you will assign it to the request. Does this make sense to everyone? Okay. As I said, this is an acceptable solution. Nothing is wrong in this solution. But for a staff plus engineer, I would not expect this solution. Okay. Now, updating fails, all of those codes, those will be a very edge cases, right? Obviously, you're going to mark it as update, and that is going to be true or false. By default, they'll be false, they'll be marked as true. So all those things like service fails and everything, that's a rare condition that happens. In general, we'll be making the service like that, the update would be successful. This is an acceptable solution mid-senior. Nothing is wrong with this approach, by the way. But for a staff plus level, I would not expect this solution. I would expect a better solution. An even better solution could be, but again, even if you say this, it's completely fine. Nothing is wrong with this. Even better solution could be, I can create a Redis in memory here. And what is that going to do is, this is extremely fast in memory, which will work in, let's say, handles a TPS of up to 100K to 1 million, depending upon how better you have implemented this. This in-memory data or in-memory sort of small memory of database, it's just going to keep this, let's say, key ID and just the key ID, nothing else. Either you can mark it as true or false or something, which is fine. That's it. Okay. So it's just going to store the key ID there, whichever key ID has already been used. Keeps track of already been used key ID. Okay. So next time your service call happens, your request comes, check in Redis memory. If something like this, if not memory dot contains, because it's just a hash map here, that particular key ID Then you're going to return that key ID. And since it's going to be extremely fast, being in memory, my time complexity would remain big of 1 here. Okay. Again, you don't need to go into that deep of a solution depending upon what role you are interviewing. This is what I would expect from senior or maybe staff or leads kind of roles. That's something I would expect such kind of this. So expectation is different for each role. This is not a bad solution. I'm not saying it's a bad solution any all. Yeah, the only pivot thing that you would have to talk about is you are changing the DB schema by creating a new column, number one. And in that new column, TTL can be very short. TTL can be, let's say 24 hours or 48 hours, whatever that is. Okay. Anyways, and then you can further optimize based upon every 24 hours. I can refresh those values. But coming back to this is not a wrong solution. There is nothing wrong with that. I'm clarifying this again here. Even if you give this is a completely fine solution. If you want to do this solution, that is also good, but that is expectation is you have to go deep dive and understand how this works internally. Okay. Yeah, that's what I'm saying. The moment you got any memory being used, you're updating the Redis as well. Since it's a Redis in-memory implemented, it's extremely fast, almost real time. Okay. This use case which we are talking about here will not make much impact here, but this will make a lot of impact when we'll talk about the Uber system design. So here, even if you don't give this answer, completely fine, nothing is wrong here. Again, I went too technical deep into it, repeating this here. This solution is good if you mention it, equally good if you don't mention it. The solution which we'll talk about here, which will not make much of a difference for this use case, but will make a very big difference when we'll go to the Uber system design, which we are still yet to go into a long time. The approach is repeating again. I'm going to keep a simple Redis in memory. That Redis in memory is just scalable enough to 1 million TPS, so I'm not worried about, and this anyway is a very small scale. What it's going to do is any key ID which is already been used or any key ID which is generated as part of a response, before you give the response, you put that into the also put it in the Redis memory. Next time a request comes, it will check in the memory whether that key ID is present or not. If that key ID is not present, that is when you return that key ID. That's it. That will make sure you are not giving already used keys to any other request. This is also a fine approach. This is also a fine approach. No difference. Okay. You have to deep dive for sure. That's why I said my expectation is from a staff plus level. So once you go that expectation means you have to know about how Redis internally works. Okay. All right. See, majority of the time they may ask or may not ask. I'm not saying with guarantee they would ask. If you're staff plus, you would definitely know about how Redis work. Even a senior or lead, you would definitely know about how Redis works internally. Okay. It's something which you have been probably using for a long time. So should be synchronized across servers where KGS is hosted. It has always been synchronized. It's in memory here, right? Wherever KGS is hosted, that's where you're giving the response. That's why it will be synchronized. Okay. All right. Keep the KGS synchronized with either Redis or creating new column. Both solution I talked about here. Now coming back to this, guys, this was unrelated to concurrency, nothing to do with concurrency. This is just talking about how we do not use the already used keys. Okay. Now coming to the elephant in the room, which is concurrency solution. How will you take care of this concurrency solution? Multiple requests comes, same key. How are you going to give response to that? All the concurrency situation, for example, this one, or take an example of Ticketmaster, Booking.com, all of these are same problems. Essentially, all concurrency problems are same problems. Okay. Now there are multiple ways you can solve in it. In this use case specifically, doesn't make much sense to go deeper here because I want to go deeper in the Ticketmaster case study because then we will talk about all the concurrency problems. Okay. In this case, concurrency is literally least of my issues. It's a very simple case study that a very simple explanation would do it. But to tell the solution, this is how we solve measure all the concurrency problems here. One way is you introduce row level locks. Okay. What is row level locks? That is called synchronized block and assign locks on read. Okay. While request one is given access to write, nobody else can write in it. Okay. Those synchronization based lock that you're going to do, you can write a simple code for writing that synchronization block as well. What exactly that is going to do is take an example of when you book a ticket, try to book a ticket, you are given 10 minutes to do the payment and complete and whatever it is. For that 10 minutes, if somebody else try to say it for other users, that seat will be gray. All agree? And by gray, I mean not available. And by green means it's available. No, nobody else can write. People can still read, right? Think of a ticket booking or let's say movie ticket booking. So in a movie ticket booking, somebody logged in and they selected a seat, but they have not done the payment yet. They still have 10 minutes to do the payment, 5 minutes, 10 minutes, depending upon whichever system it is. For those 10 minutes, if you see the screen or some other user see the screen, they would see that seat is not available. Okay. Although the seat is temporary on the hold part, but that seat is not available. Okay. If that seat is not available, if the payment goes through, if the transaction goes through successfully, then it will remain not available. But if that does not go through successfully, then it would become turned back as available. This part is what I'm referring. So other people can still see the screen, right? They can still see the seat. It's just that it's not available to them. Let me write down here. That's why I don't want to go too deep into it because it makes sense to go deep into the ticket master. But anyways, once we'll go back there, we'll discuss this. A, if transaction is successful, seat will remain unavailable. If not, seat will become available again. Everybody clear with this? Okay. These kind of problems, be it in this problem, be it in the ticket master, where it is actually a problem. How do we solve this problem statement is keeping upon a row level logs. That is one way of doing that is. Okay, we can use one level logs. Another way is we use Redis OCC. Okay, operational concurrency lock. Okay. So by default, Redis provides us OCC, which is operational concurrency lock, and that will take care of such transaction which is dealing with a very high scale. Remember what did I talk about? Redis is easily scalable up to 1 million TPS depending upon how you've actually configured it or inbuilt it. Okay, there are many inbuilt features that you can do it here. So in this use case, I don't even need to talk about it. And even if you don't talk about, that's completely fine. Even if you talk about row level logs, that's more than sufficient here. Okay. So, but I'm just telling you the answer. The approach that I'm going to discuss in the ticket master will go there. Then we'll go deep dive into the OCC. What are OCC? How do they work? So on and so forth. Okay. But for this use case, introduce row level logs is completely fine. I'm not having such a big scale that I need to worry about actually going to OCC or concurrency logs and all of that. Okay. Somebody answered optimistic logs. That is also a good solution. You can talk about optimistic logs here if you want to. But again, those kind of problem statements or these kind of solution makes more sense once we'll move to the ticket master part. Okay. For this use case, this is more than sufficient. Come on, guys, quick in the chat. Everybody clear so far? Quickly give me clear in the chat. Okay. All right. So far, we are good with the key generation service idea. We talked about some of the problem statement which key generation service has solved for the hashing approach. Some problems with the, not problems, deep diving into the key generation service, what can be the possible caveats? We talked about that as well. Now for the deep dive, is key generation service introducing any problem in my design? If it is, how do we solve it? Okay. So next part is this key generation service is a separate database. Remember that. One database is storing your mapping of long URL to short URL. This key generation database is the offline generated short keys, which is 6 characters. I hope everybody is clear with this. There are two different databases we are talking about in the system. Long URL, short URL mapping, however you want to implement that. Second is, that is our primary database, by the way. The second is this offline generated keys of 6 characters. Okay. Now, since this is an overhead in our system, overhead in the sense it was never before in the previous design, we understood something is wrong with the hashing approach. That's why we implemented this. And because of this implementation, now we got an additional database to implement. So what should be its size? Let's talk about it. 6 characters per key, 60 billion. If I'm going to stick with the 6 characters, unique keys. Multiply that 400 GB of memory. So my size of key database for 60 billion unique keys, which is way more than what I'm going to actually need it for 5 years, is 400 gigabytes. 400 gigabytes is not a very large space when it comes to SSDs and memories. Even a simple SSD can store this. Okay. So size wise, I'm not a big constraint about, but something else I'm constrained about is key generation service a single point of failure in my system? Yes or no? Is key generation service a single point of failure in my system? Yes or no? Come on, guys, quick in the chat. Let me see if it's the time to show the second diagram and the third diagram. Okay, I think now it's the time to go for the second diagram. At least the phase 2, then we can go to phase 3, then phase 4. Okay, cool. Coming back here. Before I answer this, let's talk about this guy. Now we can talk about phase 2, HLD with key generation service. Okay, so first diagram that we talked about for the phase 1, that was with the hashing based approach, basically the encoding based approach. Let's look at the second diagram with the key generation service. Then we'll continue with the discussion of single point of failures. Okay, SPOF in short. Let's take this image. Let's go to phase 2, key generation service. Let me share my screen real quick. There you go. Everybody can see my screen, I'm assuming. Let's quickly go ahead. Let's discuss about it. Pretty much whatever I need to discuss is already there in the diagram. This is a client. There are two kind of databases I'm again repeating. This is your primary database. This is your key database. Key database, offline key generation. Okay, whatever is happening offline here, this key generation service is responsible for multiple things. Make sure everything is unique and make sure that it is updating in the key database. Okay, also make sure however we hang it in the synchronization logs and all of these things will be taken care by the key generation service. Client make a request with a long URL, right? Goes to the application server connects with the key generation service will give one key that, hey, I got this key available. This database will keep a mapping of this key which is coming from here, which is short, and the long URL service, and give the response back to the client. This part clear to us? This is the flow we discussed so far. Everybody clear with this? Okay, cool. If everybody clear, let me clear my drawing. One moment, guys. Let's come back here. Okay, let me answer questions in the chat. Hashing was introducing latency, but so is key DB generation service, implementing logs, etc. Do some latency will still be there. No. Okay, understand this. Hashing was created it on the go. There's a difference between the two. Hashing was creating it on the go. A request come, now you create a hash, now you attach that mapping, then you give the response. Key generation service is offline key generation. I already have that bucket created, come with the request, pick any value in the bucket, give the response. It's not the on the go part. It's not the latency part. Yeah, concurrency case, these are edge cases. I'm not saying that concurrency will never happen. Concurrency will happen. In such cases, there would be when everything comes at the exact same timestamp, then we need to pivot about which we are going to use, which we are not going to use. But in general, if sequential calls are coming, forget about the case of concurrency for a moment. A request comes, it doesn't need to wait for on the go of something. The key is already available. Attach the key, put that into the DB, give the response back. Okay. That's what the latency problem we are talking about. Why we need another database? In the same database we can have different tables, right? It's not about the different tables. Okay, since you asked this question, that's a good question that we talked about. See, you can have one database, you can have thousands of table in it. Okay, tables, let's put it this way. There is a principle called isolation of concerns. What do you mean by isolation of concern? Every different type of database or every different type of data which needs to store should be stored in a separate server, should be stored in a separate database. Okay. The purpose of key generation service is to generate the keys. That's why I prefer to use a separate key database for that. All the isolation logs or transaction logs I need to implement, I would implement on that database. I don't want to implement, and by the way, the logs are implemented on that level. I don't want to implement on a different database which is just responsible for mapping out short URL versus long URL. Reason number one. Reason number two, if my scale is such big enough, in this case it is not, but when my scale is such big enough and I need to horizontally scale both these databases, it makes much easier that I can scale this database versus that database. So once I got two separate databases working for two separate functions, I can scale them horizontally across different multiple machines. But if I kept them in one database in two different tables, and then I need to horizontally scale, that is going to be a very big problem for me. Okay. So as an isolation of concern, always remember, and that's the whole idea of creating multiple services. You can ask like, I can keep every logic in one service. Why do I have to divide microservices? The whole idea of dividing into multiple services, each service is horizontally scalable. Okay. And each service is separate from what it is doing. Even that key fails key DB, so this URL DB won't affect. Even that fails, so this URL DB, yeah, that's point of horizontal scaling I talked about. This key DB is for short URL, yes. If yes, then how uniqueness is maintained with timestamp and user ID. Okay, let's come back here. The timestamp and user ID, that was based upon the hashing approach, which we discarded. So there's no point of user ID and anything. Every request comes, there is a key present here, pick that request. That's it. That key will be generated unique. That's the guarantee of key generation service. Okay, cool. All right, guys. Now coming back to the part that we were discussing here. With this current approach, is my key generation service a single point of failure? Read operations would go through even when write operations KDB is down. Yeah, read operations will still go through, right? What algo is getting used in key generation service? So key generation service, we can talk about any of the application layer logic you can use. There's no specific algorithm like hashing here. What we are doing is we're just creating those 62 characters. We're creating combinations of that. It's an application logic code, no algo as such. Okay. All right. Coming back to this. With this current logic or with the current diagram that we talked in the phase 2, does key generation service makes me a single point of failure in our system? The answer is yes. Because if a new request comes, if key generation service is down, in that case, you will not be able to get a mapping for a new URL. Will my write call work? No. Will my read call work? Yes. My read call is served from the primary database. My read call has nothing to do with the key generation service. Okay. The correct answer is yes, it is. My read calls will still work fine. Still work fine because they are being generated from primary database. But my write calls will not work. Okay. So what's the solution for it? If you identify that key generation service can be a single point of failure, yeah, read call means existing short URLs, which has a mapping in the primary database. Okay. If you identify that your key generation service can be a single point of failure, how are you going to solve it now? Correct. Multiple ways to do that is first thing first, whenever such a critical, okay, sharding has a different use case, guys. Replica and sharding are different things. Sharding is data partitioning. That's what we discussed in detail about data partitioning, horizontal versus vertical versus list based. Data partitioning that I need to do, that is what we call a sharding, basically horizontal part of it. Okay. Creating a replica of something is a different part. Okay. Just wanted to make sure that you guys are clear. A replica means I'm getting copies of it. So if one thing goes down, I have other replicas which are working. Sharding means I'm distributing across multiple machines. And that is for the database part, not for a service perspective. What we can do is, since it's such a critical service, we can create replicas slash secondaries, whatever you want to call it, of my key generation service. So whenever the primary service is down, standby service will be able to generate and provide keys. Okay. And on that note, how do we perform the key lookup? And then we can talk to our final phase 3. How to perform key lookup in this case? What do? We can look up the key in our primary database to get the full URL. And this is where, once you're getting the full URL, this is where exactly your call to the TinyURL or that particular service is happening. Okay. Redirection part basically. Redirection. And two possibilities. One moment, I'll answer a question. If it's stored in the database, send the stored URL, which is long URL. Okay. All right. So your write call works like this. Google.com. You created tinyurl.com. And let's say 1, 2, 3, 4, 5, 6. Now, when you go for this part, this is your right part. Once you go to this part, and this will go back to google.com, this is the read part. Okay. Now we are good to talk about phase 3 with the replica. But before that, I'll answer some question in the chat. Okay. All right. Standby to be hosted in different availability zones. Who takes care of the failover? By default, the service will take care of it. Okay. Standby will always be there in the different availability zones. If you're using S3 as a service or some other database as a service, they will take care of that. Most of the service will have the replicas created, by the way. Okay, and you can decide the number of replicas you want to configure. Okay, failover strategies are determined by that. Little optimization, we can keep unused key in Redis as well. So we can save db call to get query. We'll go to it. Our design is not complete yet. Okay. Furthermore, optimization, partitioning, all of these things we have to talk about. Okay. But whatever discussion that we had so far, let's talk about this. Based upon that, the final diagram that we would like to go ahead, and then we can do optimization, of course, is this one. The phase 3 one. Okay. Yeah, these notes are shared in your Google Drive folder or LMS portal, whatever that is. I believe the link is already in your shared channel. I'll give you some time to go through it. Let's take 10 seconds to go through it, then I start explaining it. Just look at every component, understand every flow first, and then start explaining it. Shared channel is your WhatsApp channel. Okay. Alright guys, 10 seconds are over. Now let's go through the flow one by one. There you go. Client comes with a request. Two requests can become, I want to get a shortened URL or I want to create a Excel long URL to short URL. Server will come. Obviously, we'll have a database. There's going to be a primary database, which is going to keep a mapping of long through short. And there's going to be a key generation service component here, which we talked about in the previous phase 2. Key generation service will have a key generation database. This part here, this goes a connection here. Now what will happen is if two cases, a long call or a short call, right? A long call happens means a request comes, I want to convert a long URL to short URL. It will go to the server. From server, it will go to the key generation service. Key generation service will give a key immediately available. Primary database will map that key, give the response back. First, it will update in the cache also, then give the response back to server, goes back to the client part. Second use case, a client will ask for a short URL redirection happening. In that case, I don't need to touch the KGS component here. The URL redirectioning will come from server. First, it will look up in the cache. If it is not available in the cache, then it will look up in the database, find that mapping, return either if it is present, return the response, otherwise it will return the error here. Redirection part, write call versus read call, the end-to-end flow, everybody clear? The write flow, the read flow, everybody crystal clear? Okay. This is pretty much more or less our final diagram, right? But there is a bit more further deep dive that I want to do it. For a URL shortening service, it's a very simple case study. Not a lot of interviewers wants to go into deep dive of it. This is something that they're looking for at the end of it. So the pivot elements to talk about is problem with the encoding approach, right? How do you fix that encoding approach with the key generation service? How do you take care of key generation service being a single point of failures and so on and so forth? Concurrency log based bit of those things. And more or less, this is one of the easiest case studies to go forward to. But I am going a bit further deeper down to talk maybe 10 or 15 more minutes to talk about it, and then we can close this case study. So let me close this one first. One moment, guys. Let's go to Sublime Text. Okay, back in Sublime Text. Instead of Redis, we are using cache for speed up of process write. Redis can be used as a cache as well. So you define cache where we are reading for the values. So that cache can be of anything. It can be Redis, it can be meme cache, whatever you want to implement. Okay. All right. Now moving to some other part, which is data partitioning. More or less, this is what is required or expected in terms of a URL short design case study. But talking some of the part, data partitioning and replication, let's talk about that. Our scale is not that big that we actually need to partition it. But imagine if I have to scale out our database, we need to partition it so that we can store information about billions of URLs. Okay. Then the question would come, what should be the partitioning schema? Partitioning strategy slash schema. Remember we talked about multiple strategies, range-based partitioning, hash-based partitioning, etc., etc. Come on, guys, quick in the chat. Okay, cool. That's what we're going to discuss now. So what should be my partitioning schema or strategy? Let's go one by one. If I go with the range-based one, range-based partitioning means my short URL contains 6 to 8 characters. So we can store URLs in separate partitions based upon the first letter of the short URL. Okay. Let's say save all URLs starting from A to partition 1. One moment. And let's say starting from B, partition 2, and so on and so forth. So A to Z 26, A to Z 26, 0 to 9, and total becomes 62. So that way I would have total number of partitions to be 62. Do you see any problem with that? If I do the partitioning based upon the first character or the first letter of the short URL, do you see any problem with that? Okay. To your question, system is present in US. From India, we are trying to access the service. We'll get more latency. Okay. Very subjective question. Let's deep dive into it. When you say system is present in US, what do you mean by system there? Do you mean the database is there, the data center is there? What exactly is there in the US? Part one. Part two, when you say trying to access from India, the request is not going directly from India to US in the first place. In general, any global service you want to build, the way it is built is you would have different data centers across the world. On top of the data centers, you would have the CDNs implemented. So whenever you first make a request to any server, it will not directly go to the database of that server. It will go to the different data centers which contains replicas of that database. Okay. If I give a very simple example to understand, when you play Netflix movie in sitting in India, Netflix would have its primary database, which is stored in, let's say, California, and it has data centers across the world which will contain the same replica of that primary database. Okay. Once you make a request from India, it will first hit to the CDN part. So it will try to find whatever is the latest data center available near to you. In India, I think it's stored in Mumbai. I'm 99% sure. Do check one more time, but I think it's in Mumbai that I can assure about. So your request will go to the Mumbai server. Okay. And that's the information that you will get. On top of that, since they are divided across different geolocations, they are governed by compliances. That is why the part that there are some movies or some documentaries you can see in US, you will not be able to see in India and vice versa, and some other geolocations. Okay. So request from one place never directly goes to a database for a global service. Okay. All right, guys, coming back to this problem, the problem that it is going to lead is it's going to lead unbalanced partitioning, which is uneven distributed load. Uneven distributed load. Okay. Example, let's say partition 1, which is starting with A, has more short URLs. So it has high load, and starting with B has less short URLs. So it is less load. Okay. So this is definitely not a good partitioning criteria. Can you have three partition lower uppercase and digits? We can do that as well. Yeah, instead of dividing into 62 partitions, we can do into three categories also. But again, that will lead into this problem. Since you're randomly creating is, there is no guarantee that the partition containing with small characters versus capital characters versus with numbers have the exact same replica. Okay. All right. What else? What can be the other strategy? Let's talk about hash-based strategy. Yeah, I know I'm out of time, but let's see. Anyway, it will not be finished today. There's a few more things I want to talk about. Cool. Let's quickly revise what we discussed in today's session before wrapping up, and then we can continue with the next part. Pretty much we have done it. These are some extra things we are discussing about. Partitioning, DB scheme, all of those things. We have pretty much discussed that in detail in the basics, but I just want to make sure we are following the complete template so we know end-to-end idea. Okay. There is one critical component which is missing here, and that I would like to discuss in detail. That is what we call as cleanup service. Not sure if you saw that in the diagram. This is the final diagram, which is a simplified one. This is a simplified final diagram here. Okay. This is our phase 4, and this is our end-to-end diagram, how it would look like. One moment. So when we say end-to-end diagram, there is one component which we have not touched yet. That is what we call as cleanup service. Why do we call it cleanup service? One moment, guys. Client comes, goes to load balancer, goes to application server. Cache server we already know about, database server we already know about, key database we already know about, replica of key database we already know about, key generation service we already know about. Apart from cleanup service, anybody that has any doubt in this diagram, let me know. Apart from cleanup service, anybody has any doubt in this diagram, let me know. Okay, cool. The only thing that we have not talked about yet, which I will deep dive, is cleanup service. What is that cleanup service? Pretty much it's self-explanatory. There are URLs which are going to expire, right? Either we have given the default expiry times or that we have given a customer the feature to create expiry time. There should be some service which is doing that cleanup in the database. All agree? That is why you see there is a two endpoints here from the cleanup service. One is pointing to the database. Let me take this. One is pointing to the database and one is pointing to the key database. Agree? It should be removed from my key database and it should be removed from my database as well. Okay. So pretty much we know about what this is going to do, but we'll talk down deep dive about this later. Let's go back to our Sublime text. And let's quickly revise what we have discussed so far. Let me answer the questions in the chat, by the way. Creation of keys by cages service should be in scope. Not exactly. How the creation of key is going to be simply a random function to create between that. That's application logic, not in the high level design. Will we be allowed to cover spam URLs? No, not in the scope. As we are planning to store the use keys in Redis, at the end of the day, we need to mark the use keys in the DB as well. Otherwise, next day, same key may come. How do we the DB here? A bad job. A cron job would do here, yes. Load balancer to spread traffic only, right? No special logic. The purpose of load balancer is to spread the traffic and to make sure all servers are working fine, keeping track of that. All of that we discuss in the basics of system design. Key database will have unique key and key database server contain long original URL. Key database have unique key. Yes, database server create the mapping between the long URL and short URL. Okay. Yes, you will get the images. Not in the notes. I'll share that images directly in the WhatsApp channel. Okay. All right, now coming to a quick revision where we are. We pretty much 80% have covered our first case study. I'm not calling it as 100% because few things I want to discuss. And then we'll move to next case study. So starting with the defining DB schema, we started with number 5. So we have made some observations in terms of storing number of records. What's the store size that we're going to store, relationship between them, or services read heavy or write heavy. We decide the DB schema, pretty much we need two different URL and the user. Based upon the data points that we collected, my choice of database, any NoSQL database would work perfectly fine. Okay. Algorithms part we talked about. First, we think about creating an encoding based parameter, which is like a hashing. So we talked about what algorithms we can refer to here. We create based hashing, but we encounter into two issues. First, if multiple users try to access the same URL, and second, since hashing is creating some extra latency, which I don't want in my system. So we talked about workaround. First thing, if how do I take care of multiple users? I can create this as a unique timestamp that will take care of it. But the second is, in case I'm creating extra latency, I cannot solve it with hashing for sure, because hashing will definitely introduce some latency. So we pivot the approach of hashing altogether. We move to second approach called generate keys, which is short keys URL. So rather than creating it on the go, I can create it offline. So I will have a separate key generation service with a separate key database, which will take care of creating random these 6 characters. And once the request come, it is available to pick up. We talked about concurrency. We talked about the use case when it is not already used keys. How to make sure we are not using the already used keys. We talked how to make sure that we are handling the concurrency. We went into a further deep dive here, which may not be required here, but we talked about all possible solutions. Okay. Then we talked about, is KGS SPOF? Yes, it is. How will we make sure that it is not SPOF anymore? We'll create replicas in the system. How do you perform the key lookup? We talked about that. We talked about phase 3, and finally we talked about phase 4 as well. Okay. All right, guys, more or less that was our first case study, 80% completed. Let me know if you have any doubts in whatever I have taught in today's session. If everything is clear, just type clear in the chat. Okay, all good. All right, guys, let's wrap up the session here for today. I'll share the design notes, and these notes will be shared by a course coordinator, the written notes. And we'll connect in the next session, finish this case study, and then move to next case studies. How many more sessions I cannot comment as of now, considering that we are going to discuss 5 to 6 case studies instead of doing all the 10 case studies. You can assume maybe 7 to 8 more sessions, easily 7 to 8 more sessions. Okay. And depending upon how further deep dive we want to go into the case studies. Okay. All right, guys. Yes, only for HLD. All right, guys. The big case studies like Facebook, Netflix, they take easily 3 sessions. Okay. The small ones URLs we can finish in 1 or 2, but big case studies definitely take 3 sessions. Okay. All right, guys, let's wrap up this session here for today. Let's catch up in the next session. We'll continue with this and go to a new case study. Thanks for joining in and have a good one.